So at the most basic level, a function is a case where you have an xy pair, right? X represents the input. It's a function if each input only gives you one exact output. Right? So you plug x in, you get the same output every time. In terms of graph, that's the whole vertical line test, right? If a vertical line only hits your function once, graph once, it's a function. If it hits it multiple times, it's not a function, because then for that particular x value, you have more than one output. So we use f of x notation. There are some other types, but this is definitely the big one. I think it's important, though, to realize when you just look at a simple, now a lot of times you say y equals, correct? We know that y and f of x can be replaced, serve the same purpose. But let's just look at something like f of x equals 2x plus 3. Right? Nice, simple linear function. There's a lot of information here that you may not have realized. Is as we look at this, the name of the function is f, right? That's telling you that's the name of the function, right? F's kind of a generic name, but maybe you have an area formula and it's called capital A, or we'll have surface area formulas that'll be called capital S, or profit function will be P, right? You could use those to kind of identify what's going on there. Whatever's inside this parenthesis is the input variable. Okay. So in this case, it's f of x. Now, it's not going to be uncommon for us to have f of x equals, and then over here there may be additional variables besides the x. But this is our goal, is to have that as our input variable. If we have other variables, we'll learn how to deal with that. But that's something that's going to be a little bit new, I think, with some things that we do. F of x, or the expression 2x plus 3, is the output. Output. So the whole left-hand side, f of x itself represents the output, or 2x plus 3 represents the output. So what this means is, whenever you see this, this also tells us that on this graph, so that f has on its graph the point x, 2x plus 3, or you could write it as x, comma, f of x. Right? So every time you see function notation, it's also telling you there's an ordered pair and telling you where that ordered pair would be on the graph. Okay, remember, a graph is just a picture of all the solutions, all the xy pairs that make the equation or the function true. That's all a graph is, nothing else. So just again, maybe just know its name, you're identifying the input variable. I mean, if you're going to put something else in, then we know that we remove the input variable everywhere and replace something else. So if we're going to do, f of 5, well, we take this rule and we replace everywhere there's an x, we replace it with 5. So we get f of 5 is 13. Right? That means that you would have the point 513 if you were to graph that. So a lot of times if you've evaluated the function that you do have to graph, you could just graph those and take advantage of it. Okay, so from your note sheet, again, these are all worked out for you. I probably would, when we get to C, I'd probably recommend you make a note or two. It's a little bit involved. But here we have some function, f of x equals x squared minus 5x plus 8. We're asked to find f of negative 6. So again, the x was replaced with negative 6. So we're going to take this expression, this right hand, and we're going to fill everywhere there is a x, we're going to put negative 6. Now, I would highly recommend that whenever you substitute a number in for a variable, is you put that number in a parenthesis. Because here, if I didn't put negative 6 in a parenthesis, then it would look like the opposite of 6 squared, which is negative 36. Or actually, it's negative 6 times negative 6, which is going to be positive 36. Okay, if you're really good at order of operations, you probably don't need to. But if you're not, the parentheses will save you a lot of just kind of those little annoying mistakes that you make and you miss a point out of 5. But because you did something that you really knew better, but it slipped by you. Okay, so here, we're going to get 36 plus 30 plus 8. Add those together and we get 74. Right, so that means on this graph, there'd be the ordered pair -6, comma 74. We good there? Too much to it. For part B here, we have a fraction instead of a -6. We should be able to work with fractions. We don't have to like it, but so 3/2 squared minus 5 times 3/2 plus 8. And I'd encourage you, if you really avoid fractions, just try them a little bit. They get easier pretty quickly. We know that when you square a quotient, you square the top and the bottom, so we get 9/4. And then here we get minus 15/2, because we do 5 times 3. And then we have plus 8. Now at this point, I'm just going to get them all to have the same denominator. Should be pretty good from there. So 9/4, this would be minus 30/4, and then plus 32/4. So multiplied by 2/2, multiplied by 4/4. Well, look right there, there's 2 left over. 9 plus 2 is 11. So we have f of 3/2 is 11/4. That tells us that for this function f, if you plug in 3/2, your output's going to be 11/4. All right, so let's look at this one. Hopefully you remember that this is called the difference quotient. Okay. And every year as a calc teacher, we tell the pre-calc teachers, which is me this year, that we need to practice this more. This is a really important thing. It's a pretty integral part of calculus. No pun intended. But we have to evaluate this. Okay, now, there's actually 2 functions here. The nice thing is whenever you evaluate one of these, what's going to happen is you're going to get a giant mess in the numerator. Hopefully all of the second part's going to cancel out somehow. And then you're going to have a common factor of h on top, which is going to factor out with the h on bottom. Like, a lot happens, right? And it looks horrible as you're working through it, but a lot does happen here. So what I'm going to recommend we do here is first find f of x plus h, because that's really the challenging part. Okay, so to find f of x plus h, we're going to take our rule for f of x. Everywhere there's an x, we're going to pull that out, and we're going to replace it with x plus h. Okay, so we get x plus h squared minus 5x plus h plus 8. Now you do have to expand it for this to work. So we're going to go ahead and square x plus h. Remember, this is a binomial square. Don't forget your middle term, right? So it's going to be x times x, so x squared. It'll be 2 times x times h, so plus 2xh, and then plus h times h, which is 8 squared. Minus 5x, minus 5h, plus 8. Are we okay with the expansion there? Again, this term, a lot of people miss that one, so just be very careful. If you see a parenthesis with a plus sign in it, it means anything that you do is going to be really difficult. And none of our cool exponent rules are going to work because the plus or the minus kind of jams things up. So I'm going to go ahead and plug into this expression now. So I'm going to take f of x plus h out, and I'm going to do x squared plus 2xh plus h squared minus 5x minus 5h minus 8 minus, now I'm going to subtract f of x, which is our original function, x squared minus 5x plus 8, all divided by h. Doesn't look great, right? Looks like there's a lot going on, but I want you to know, now here what I did is something to help me, is I'll always put a parenthesis around the f of x plus h, and I'll put a parenthesis around f of x. This one doesn't matter. It doesn't do anything. This subtraction sign gets distributed into f of x. If you miss that, it won't work. Like it just won't. So what we're going to see now is we look at this. If we look, here's an x squared, correct? This is going to become a minus x squared. Those are going to cancel. I like to underline things as I use them. So as I cancel, I'm going to underline them. That way I don't erase my work. I see that here is a negative 5x. This is going to become a plus 5x. Those are going to cancel. This is a negative 8. Why is that a negative 8? It shouldn't be a negative 8. It should be a plus 8. For right here. Just miswrote it. So that's a plus 8. This is going to be a negative 8. Those are going to cancel. So if you notice, all that stuff canceled out, correct? And I just cancel it. You could expand it and then cancel it, but does that make sense? If it doesn't, go ahead and distribute, drop those front parentheses, and we'll see how that goes. Good. So with this one then, we look at what's left on top. We have 2xh plus h squared minus 5h all over h. Yeah. So if you notice now, there's a common factor of h. All over h. Out of room here. But and even if there were other common factors, I just want to pull the h out because my goal is just to get that one on bottom canceled. So then we get that the answer would be 2x plus h minus 5. Yep. So that would be our difference quotient. When we learn about derivatives, we use this difference quotient. We do something called a limit to it. It just changes it, so it'll look different. Okay, here for our second example, we have a of r equals pi r squared. Again, we used our naming conventions here to be helpful. Anybody know what this is for? Interior of a circle, right? I mean, I would assume. The area is a function of the radius, right? As you could say, as a function of, is sometimes how you read that instead of a of r, but as a function of. It's pi r squared. Remember, pi is a number. It looks weird, but pi is just a number, so it's a constant term. So with these, it's just asking you to evaluate some things. So we have evaluate a of 3. Everywhere there's an r, you're going to replace it with 3. So that gives you that a of 3 is pi times 3 squared, or a of 3 is 9 pi. You want to just leave pi as the symbol pi. It'll make it way easier. Later on, it's just a nice constant. We can deal with constants all day. There's really no problem with those. Those are not going to be the things that cause us difficulties, right? Constants are fine. Here, the second one is a of 2s. Sometimes you'll replace a variable with a different variable. You know, whatever. It just happens sometimes. So here, to do a of 2s, we'll do pi times 2s squared. Be careful. A lot of people see this and they write 2s squared and they don't square the 2 also. But there's a product that's being squared, so we square both parts. And that's going to be pi times 4s squared. So a of 2s is equal to 4 pi s squared. It's commutative. You could write it a bunch of different ways. Usually I put the regular number part, the weird symbol number part, and then the variables after. But it's up to you. If you do find a way to continue to write things, like a lot of times if there's multiple variables, I'll go alphabetical. It's easier to spot that, I didn't do it here, but it would be an example. But if you have xh and xh, it's easy to see that they're the same. Or if you have xh and then you have hx, you might not catch them as quickly. So you make them look similar. Here's the last part, C here. So again, we have two functions, correct? The first time, you're going to take this function, you're going to remove r and replace it with r plus 1. So that'll be pi r plus 1 squared. And then over here is just a of r, so it's just going to be pi r squared. Now, in a case like this, we need to go ahead and square that. I think something's going to cancel here. I'm pretty confident. So that gives us r squared plus 2r plus 1 minus pi r squared. So again, a binomial squared. Don't forget that. That's a big one. If you need to write it out and FOIL it, you can, but I would just probably learn the pattern. If we distribute pi, we have pi r squared plus 2 pi r plus pi minus pi r squared. So we see that these two will cancel. See lots of canceling. And that's going to give us 2 pi r plus pi. I think that's a fine answer. There may be an advantage at times to writing something like that as pi times 2r plus 1. They're both valid, they're both good. It's not a bad idea to kind of look at different ways the answer could be written. Kind of be aware of that. Okay, so for compositions, again, we're going to take an input, plug it in a function, get that answer, plug it in a new function, have our final answer. These are compositions of 2 functions. You could have compositions of 3 or 4. Sometimes in calculus, it's nice for us to like take a complicated function and make it into a composition of simpler functions. It just lets you do easier work in terms of the calculus part. One thing to remember is this worksheet does not point this out, but often instead of this format, f of g of -1, you can also see that written as f with a circle g of -1, or as, when that in parentheses, f of circle of g of -1. This is notation that you'll see for compositions also. It means the same thing. I prefer this. This seems to be more explanatory, and we can work from the inside out, but this is around. Okay, so you will see that sometimes. I think it's used, I think our book uses both. Just you want to be familiar. If I see this, I just write it like that. It's my first step. Both of them, you work from the variable out, right? This is just a little circle. It's not a times symbol. It's just an operator that we use for compositions. So, okay, f of g of 1. The first thing we're going to do is put -1 into g. So I would just write f and then a parenthesis, okay, big parenthesis. And then g says take, so what g is telling you is take the input, 2 times the input minus 1. So here we're going to do 2 times the input minus 1. Let's see, -2 minus 1, I think that's -3. Okay, now we have to evaluate f of -3, and we're back to what we were doing before. Right? So we'll put in here, so -3 squared minus -3 plus 1. Be very careful, especially when you're plugging in a negative number. You know, sign errors are common. They happen quite a bit. So here we're going to get 9 plus 3 plus 1, and that's going to be 13. Hey, that's even what your note sheet says, so that's good. We okay there? Okay, if you want to, why don't you go ahead and try B. We have, it's the same input, but we're just doing the opposite order. Hopefully everybody remembers that compositions are usually not commutative. If they are, it's something special going on. So we're going to do g of, so that's the outer function. I'm just leaving it there to remind myself that, hey, I'm not done. I still have to plug that whole inner number into g. So f of -1 would be -1 squared minus -1 plus 1. So that's 1 plus 1 plus 1 is 3. So we have g of 3. And then now I'm going to take that input and plug it in here for this x. So 2 times 3 minus 1 is 5. So obviously these are different, right? Order matters. Now we're going to go ahead and work this out because it's what it wants us to do. But actually, we can verify this is not true because we just showed a counterexample. Like, see, it doesn't work. So that's all you'd have to do to actually show that something's not true, is to show a counterexample. Like maybe you learn about multiplication, you're really excited that 2 times 2 is 4. And you're like, you know what, I think multiplying 2 numbers is the same as adding them. Well, it's not. Counter examples would be like take 1 and 3, right? 1 times 3 is 3, and 1 plus 3 is 4. Counter example. But that's not what they want us to do. So to do this, let's just go ahead and find a single rule for each side. Because one option we had is when it asked you f of g of -1, we could have found a rule for f of g of x, a single line rule, and then plug -1 into that rule, and it would still give us 13. So that's if you have a bunch to evaluate, or you're looking for a graph of a new function, or the graph of the composition. But with this one, to do f of g of x, we're just going to replace g of x with 2x minus 1, right? That's what it's defined as. And then we'll go ahead and plug that in everywhere there's an input variable, right? So this input variable is this x, which is really just a dummy variable. It's just a placeholder. It's like that little dashed box they give you in grade school. You have to put the number in it. It's just a placeholder is all it is. So we get 2x minus 1 squared minus 2x minus 1 plus 1. And then we're going to get 4x squared minus 4x plus 1 minus 2x plus 1 plus 1. So 4x squared minus 6x plus 3 would be our new rule. We okay with the algebra there? Now if we look, if you put -1 in here, you're going to get 4 plus 6 plus 3, right? 4 plus 6 plus 3 is 13, which is what we found there. So you always have that option. You could write a new rule, or you could just do the single number. To check the other side, we'll get g of x squared minus x plus 1. Again, I just replaced f of x with x squared minus x plus 1. And now our rule for g tells us to take 2 times the input minus 1. So 2 times the input minus 1. Again, we pulled that x out, replaced it with a parenthesis. 2x squared minus 2x plus 2 minus 1. So 2x squared minus 2x plus 1. Again, just to verify, if you put -1 in here, you'd get 2 plus 1, which is 5. Now we can see here that these are very different expressions, right? Because consider the graphs would be different. They're just not the same. So we showed their formulas are not equal. But it's, again, there will be commutative cases, but it's pretty rare. It's pretty uncommon. All right, our last example here today, we want to talk about functions, talk about piecewise functions. So, and they are like they sound. It's pieces of 2 or more functions that are put together. It's like Frankenstein's monster of functions, right? A little from here, a little from there. So I think what's confusing sometimes is how they're written. Okay, the function's called f of x. We got our big brace here, and there's a couple formulas. But actually, the first thing you want to do when evaluating is you have to look all the way to the right here. Because this is telling you we use this top formula when x is greater than or equal to 0. We use this bottom formula when x is less than 0. Okay, so 2 different formulas based upon what where x begins at. So to look at, so again, you look over here, figure out which one you want to use, and then once you figure out which one you use, it's the same as evaluating any formula for points. So for f of 5, well, I look, is 5 greater than or equal to 0? Sure is. So that's my equation. So that's going to be, so f of 5 equals 5 squared minus 3, which would be 22, correct? So if I were to graph this piecewise function, the point 5, 22 would be on that piecewise function. Good? All right. Here we have f of 2 minus f of -1. You could do each of these separately, get answers, and then subtract them. That would be fine. This one I probably do it all at once. Maybe I'll use braces or brackets or something to show that I'm working with two different functions. So f of 2, so I look here, as 2 less than 0, nope, but 2 is greater than or equal to 0. So for the first one, I'm going to say 2 squared minus 3, bracket. I just keep it all in a bracket there, just as an idea of kind of organizational idea. And then f of negative 1, well, negative 1 is less than 0. So that will be bracket 2 times negative 1 plus 1. Everything look okay so far? Yes?
Why didn't you turn the negative 1 into a positive 1 and then just put it with the first?
Well, we have to leave them the way they are. We can do nothing with these two. Like, we can't subtract those. Like, if you have f of something, it just means you got to evaluate the function. It's just like if you had, you know, the sine of 2 minus the sine of negative 1, which would be kind of a weird problem, but you just got to deal with them and do it that way. But no, there's no convention. This is a negative 1 that we're plugging in, so there's no absolute value or anything. It's just a negative 1.
Yeah. Okay, so it like doesn't.
Okay, so as we do this, we get 4 minus 3, which is 1, minus, let's see, and then this is minus 2 plus 1, which is minus 1. Again, you always have to be very careful of our double negatives and all that good stuff. So we get 1 plus 1, which is 2 for our answer there. Lastly, f of 1 of 1. This one's, we'll see, I like this one. So the first thing we do is f of 1, correct? To do f of 1, do we use the top or the bottom equation? Top. Okay, so we say f of, and then we get 1 squared minus 3 in this parenthesis. So 1 squared minus 3 is negative 2. Here's where you have to be careful. If we do f of negative 2, do we use the top or the bottom equation? We use the bottom, right? Because that's where it's defined, because negative 2 is less than 0. So 2 times negative 2 plus 1, negative 4 plus 1 would give us negative 3. And that's a piecewise function. Since we have this here, we're going to have to sketch these or take piecewise functions and write functions for them. So let's just go ahead and see how we would graph this just real quickly. The big thing to determine is really what you're going to do is you're going to basically make two XY charts. Okay. You're going to make this one, which is going to include 0 for x and then things to the right of 0, bigger than 0. And then you're going to have this one, you're still going to include 0 in that table and things to the left of 0. Yeah, now it will be an open circle on this endpoint, and this endpoint will be a closed circle. The reason people miss this is they read x is less than 0 and they think, oh, I just need to go to negative 1. Well, there's a lot of numbers between negative 1 and 0 that we have to account for, and that an infinite amount of numbers. So we have to account for those. So in order to sketch this, kind of the process I would use is for this first function. Now I could use the fact that it's a parabola and it's translated 3 to the, to the right if I wanted to. That would be fine. But you also could just plug in 0, 1, and 2 and kind of go from there. And I know that this is going to be a closed circle, right? It's like a bracket, a closed interval. It's going to be included in the point. So if you were asked to find f of 0, you'd use this rule, correct? Because it's equal to 0. So this will give us negative 3, and this will give us negative 2, and that'll give us 1. So we have 0, negative 3, 1, negative 2, 2, 1. So it's just part of a parabola, right? That's what we're looking at there. It was actually shifted down, wasn't it? I said side to side, shifted down. Okay, so we have that. But it's going to be a closed circle, so I need to really, if it is a closed circle, you want to make it obvious that it's a closed circle. These dots over here, these are just dots because I needed something to show me where the curve went. Those don't really have any significance. So you don't really need to have those there. They're okay if they're there. But this one needs to be obviously a closed circle, would be the thing to look at. Now for this function, again, we're going to use our values. We're going to go 0, -1, -2, because we're going left of 0. But this will be an open circle. Okay, and we have to go all the way to the open end of that endpoint to put that open circle. Don't stop at -1, which is generally how people goof it up. So this gives us 1, -1, -3. So there's our open circle. We want it to obviously be an open circle. And then let's see, -1, 1. And it's a line, so I'm not going to get a bunch of points here. So it'll look like that. And if it's actually a piecewise function, it should pass the vertical line test, right? And it does. Even here, it only hits it once. It hits at the closed circle. Okay, so from your graph, it should be obvious that f of 0 would be -3 because there's a closed circle as opposed to 1. Okay, now, we kind of alluded to this the other day. Sometimes we'll talk about behavior as you approach something. So like this one, as we approach 0 from the right, we'd say it approaches -3. But as we approach 0 from the left, we see it approaches 1. So we get to limits, we'll deal with what to do in that situation, what that tells us.